Welcome to this standalone lecture on the pigeonhole principle. Let us look at a puzzle which we will solve using the pigeonhole principle. So what we want to show is the following. Show that there exist two people in India who have the same number of hair on their head. So at any point of time, you can find two people which have the same number of hair on their head. This seems like a very, very strange thing to ask. How can anyone possibly prove this? We will see. We can say much, much more than just two people. We can say much more. So let's get started. So here's the informal version of the pigeonhole principle. We have three cages. I'm just illustrating the informal version. There is a more general statement to be made. But right now we have three cages and four pigeons, strange looking pigeons, but just think of them as pigeons. And each pigeon needs to go in one of the cages. One is free to put them in any cage one likes, but one has to put them in some cage. Not that I encourage putting animals in cages. This is just an example. Actually, I'm vehemently opposed to putting animals in cages. So suppose we decide that this one goes here, this one goes there, maybe this goes there, but then it turns out that there will be a cage which will have to accommodate more than one pigeon, right? So a general statement that we can make here is the following. Suppose P pigeons are to be kept in or are to be put in C cages if the number of pigeons exceed the number of cages, then some cage must accommodate what's the spelling of accommodate? I don't know. Must accommodate at least two pigeons. It's a very, very commonsensical statement. All right. So that's what is going on here in this example. Okay. In our example, P were equal to 4 and the number of cages is 3. That was our example. Okay, one can formalize this. This is an informal expression because pigeons and cages are not mathematical objects. So one has to say it formally if one likes to, which I like to. So the formal statement is the following. Suppose x and y are finite and non-empty sets. We are given some function from x to y. If the cardinality of the domain exceeds the cardinality of the target, then f is not injective. Right? That's what the previous statement is really saying. This is the set of all pigeons. This is all the cages. This is f is an assignment of a pigeon to a cage. So any such assignment is non-injective. What does that mean? What does non-injective means? So if you look at my primer on functions, non-injective means there exist two distinct elements in the domain such that they have the same image. So these two pigeons go in the same cage, right? So that's the formal version of what we just said. Right? This is a version of the pigeonhole principle. What we have written here is a version of the pigeonhole principle. If you want to prove it mathematically properly, then you can resort to the well ordering principle, but I don't think there is any need to prove it. All right, so let's use it to solve our puzzle. So in our puzzle, we have all the people in India, and we want to show that two of these people have the same number of hair on their heads. So what one can do is, so first the formal description of how to solve it. So let X be all people in India and Y is equal to 1, 2, 3 up to, let's say, 10 million. How much is a million? I think 6 zeros. Some big number, 10 million. I should also put a 0 here. We'll see why. So define f from x to y as the function which counts the number of hair on the head of a given person. You pick a person, what does f do? It just tells you the number of hair the person has on his or her head. Right? Now, this is a huge set. We know that the cardinality of this, so the cardinality of x is greater than 1 billion, which is 10 to the power, I don't know how much. Let me see. So I think it should be this. It's a huge number. Who cares how many zeros? Okay, it's just bigger than what I have written here. Why? Because any person on planet Earth cannot have more than so many hairs. Can have 0 hair, 1 hair, 2, 3, cannot have more than that. So this is a well-defined map. If I had chosen just 10, if this set were just consisting of 10 integers, then this wouldn't be a well-defined map, because obviously there are people who have more than 10 hair on their head. But we have chosen a sufficiently large number so that this is a well-defined function. A lot of things here will be hungry, meaning nothing will map to them, because this is a very, very big overestimate, but a reasonable number still. So you have a set of size greater than 1 billion mapping into a set of size less than 1 billion, because it's just a set of size around 10 million. So f is non-injective, and therefore there are two people which have the same number of hair on their head. That's a complete argument. Or if you want to think in a more informal fashion, you can imagine 10 million cages, and on every cage you send a person depending on the number of hair the person has on his or her head. So label the cages from 1 to up to whatever 10 million, and every person has to now go to in one of these cages. Since there are fewer cages than the number of people, some two people have to go into the same cage, and that's it. Okay, so that solves this puzzle. And now let us look at a more general version of what we have done so far. So this time what we have is, again, 3 cages, but 7 pigeons. Okay, so let's try to put them in various cages. Maybe, whatever, just do your scheme. And you will find that no matter what you do, there will always be 3 pigeons in some cage. Meaning there will be a cage which will be accommodating at least 3 pigeons. Okay? So here is what is going on. Say P pigeons are to be put in C cages, then some cage must accommodate at least P by C. You consider this number. Let me write it here. P by C. And then you take the ceiling value. So I will recall what is the ceiling value, something that you read in high school. So some cage must accommodate so many pigeons. Okay. So what is the ceiling value? Recall that. Ceiling value of a real number x, so x is some real number. Ceiling value of x is the smallest integer which is at least x. Okay, so for example, what is the ceiling value of 2.1? It is equal to 3 because 3 is the smallest integer which is at least 2.1. 4 is not because 4 exceeds 3. It is not the smallest integer which is at least 2.1. What is the ceiling value of 2? The ceiling value of 2 is 2. 2 is the smallest integer which is at least 2. Okay, so this is our general statement, and what is happening in this example is we are having 7 pigeons, 3 cages. So if you take the ceiling value, you get, it's ugly. So if you take the ceiling value of 7 by 3, you get 3, right? So it checks out. And the reason why this is true is very simple. Basically, if you want to prove this, what you do is you write P as C times K plus R, or let's say Q, C times Q plus R, where R is in this region. So this is basically division with remainder. C is the divisor, Q is the quotient, R is the remainder. So remainder lies in this range. And just looking at it should make it clear that if suppose R were 0, then you must have at least Q pigeons in some cage, which is the number same as P by C. And since P by C when R is equal to 0 is an integer, ceiling of P by C is just P by C. But if R exceeds 0, then you would have to do P by C ceiling, strictly the ceiling. You cannot just write P by C because P by C is a fractional value. So that's what's going on here. And yeah, again, if you want to really prove it, you can use the well-ordering principle on the number of pigeons or the number of cages, whichever you like. Number of pigeons would be most convenient. Okay, so this is the informal description of the general form of the pigeonhole principle. And here is the formal description of the general form. So again, x and y are finite non-empty sets. F is some map from x to y. Then there is an element y such that the fiber above y, which I will recall, has size at least the ceiling of this number. So let me make it neater. Yeah. So that's the theorem. And now what is this expression meaning? So recall that F inverse y, this is supposed to mean all these elements in X which map to Y. Okay. So this is what is being said in the informal version. This is your total number of pigeons. This is cages. And there is at least one cage. There is one cage which accommodates at least so many pigeons. Okay, I hope you're able to correlate. So now we will move on to examples. We will see two applications of this. So first application. Suppose we have 8 integers. Then we want to show that there exist I and j which are not equal, such that the corresponding difference is divisible by 7. So these integers may have repetitions. We are not insisting that they are pairwise distinct. Repetitions are allowed. And now we want to show that some two of these numbers have the property that their difference is divisible by 7. Okay, so we will show this, and before we show this, just we make a small note that if x and y are two integers and n is some other integer, let's say it's positive, then x minus y is divisible by n if and only if x and y leave the same remainder when divided by n. So it's a very small note. And now here is what we will do. So let x be the 8 indices and y be equal to all possible remainders when you divide something by 7. Right? So if you divide a number by 7, you either get a remainder of 0 or 1 or 2 or up to 6. And define a map which takes an index and records the remainder of the corresponding number modulo 7. So I is mapped to the remainder when AI is divided by 7. So that's the map F, and since this has more cardinality than that, this has cardinality 8 while this has cardinality 7, there exist two things here which map to the same element here, and hence two of these numbers leave the same remainder modulo 7, meaning when divided by 7, and hence their difference is divisible by 7. Okay, so that's a very nice application. And now finally, we have one more classical problem that we will look at. So we want to show that amongst any group of 6 people, there are 3 of them who are mutually friends or mutually strangers. So of course, this requires some assumptions. So we are assuming that given any 2 people, either they are mutually friends, meaning both are friends of each other, or they are mutually unacquainted. Nobody knows the other person. So if there were a celebrity in the group, then you could say this fails. People may know celebrity, the celebrity may not know any of those people. So such sociological assumptions are made. Under those assumptions, we want to prove this. Okay. So here is what we will do. We will think of the 6 people as dots. This is the first person, this is the second person, third, maybe I'll make it here, third person, fourth, fifth, and the 6th one. Okay, so we have 6 people, and now we want to show that 3 of them are either mutually friends or mutually strangers. So what we will do is, if two people are friends, then we will draw a blue edge between them. We will connect them by a blue line segment. And if 2 people are strangers, we will connect them by a red line segment. Okay. So now just focus on this first guy. There are 5 edges emanating from this guy. Some are blue in color, some are red in color. Okay, so 5 pigeons and 2 cages. Hence, there must be some color which is accommodating at least 3 edges. That's the pigeonhole principle. So, without loss of generality, let us say the the red color appears at least 3 times. Let's say it looks like this, meaning this guy is strangers with that, and that. I mean, this guy is strangers with him, and with him. It could be that this person was emanating 3 blue edges. The argument would be very, very similar. So let's say, without loss of generality, that we have 3 pink edges or red edges coming out of this person. Okay, now forget about everything. We just focus on these 3. Suppose they were also mutually strangers. Then this would also be pink. And hence we would have a triangle, all of whose edges are pink. And hence these 3 people would be mutually strangers. So this edge cannot be pink because, or rather I should say, if this edge were pink, then we are done. So in the adverse case, this edge must be blue. So I'm using red and pink interchangeably, sorry about that. So this edge, in the adverse case, this must be blue, because if this were pink, then we are done. Same argument for this guy, because otherwise we would have these 3 as mutual strangers. So this is blue. And the same for these 2 people, because otherwise we would have this guy, this triangle, all pink. Hence this, in the adverse case, must be blue. But now these 3 people, they are all blue together and hence mutually friends. So if we assume that there are 3 pink edges coming out of it, we can find a blue triangle. And if we assume that there are 3 blue edges coming out of it, by the same argument, we should be able to find a red triangle, unless we are already done in an intermediate step. So that's it. That's the solution of this puzzle. One can write it down formally if one likes. And I hope you were able to follow. As usual, like, comment, share, subscribe, and I will see you next time.